Okay, so thank you very much for coming to another seminar. Today it's a special day. It's not on Friday, it's on Thursday because we have invited a speaker that coming from quite far. And what Victor is going to introduce because he knows him better. So thank you very much for coming and thank you very much, Kasper, for coming.
Thank you. Thanks all for coming to this seminar. We have the pleasure of having Kasper Hunnestad here today. He's postdoc at NTNU in Trondheim, and he is developing a very unique lab experiment to monitor the CO₂ movement in the subsurface in a scale experiment in a controlled way, with the idea of having insights on how to control the CO₂ in the field, as we have more and more projects in which we are capturing and storing CO₂ deep underground. So thank you very much for coming, and we are very looking forward to your presentation. So you have the floor.
Thank you, and also thank you for having me here. So yeah, the talk today will be about subsurface CO₂ storage monitoring, but in a lab scale. So this is quite different from, I guess, the usual CCS projects that you've maybe seen before, but I hope it will still be understandable. So before I go to the science part, I just want to introduce the center that I come from. So it's called the Center for Geophysical Forecasting, or CGF. And yeah, it's based in Trondheim in Norway. And we're part of the Norwegian University of Science and Technology, or NTNU. So the center is quite broad. It has people working on a lot of passive acoustic monitoring. If you're familiar with distributed acoustic sensing, that's one of the main things that we work with. But we have people working on studying whales, earthquakes, geohazards, a lot of different topics. But it's a kind of section within CO₂ gas and energy storage that I come from. And then the person, Martin Landre, is let's say the director of the center, and is a person I work with the most at the moment. He was the person who kind of conceived the idea of the CO₂ lab. And then Philip Ringrose is the person in CO₂ storage that is more the thematic leader of the work. And by the way, if you have any questions, just ask me during the talk. I prefer that you ask now and not get confused if I say something wrong or something. Anyways, so over to CCS. If you've never heard about this before, this will be a tiny crash course. So the idea is that we have a few point sources that have huge emissions of CO₂, typically cement factories, recycling centers, and these point sources are relatively easy to capture the CO₂ from. Now, once you capture it, just the sheer quantities can be quite enormous. In Norway, for example, the annual emissions, I think it's about 100 megatons of CO₂. So you need to deal with it somehow. And storing this in the subsurface is one of the most practical, reliable ways of doing that. So essentially, you condense the gas down to a liquid phase, and then you kind of ship it over to some facility that sends it underground. And the kind of central criteria is that you find some sort of porous underground formation that has a seal that is impermeable, that it prevents the CO₂ from leaking up and effectively trapping it there. In essence, what you're doing is kind of reverse engineering the gas and oil production. Instead of pumping out oil, you're kind of injecting back in the CO₂. So in Norway, this started out quite a long time ago. I think 1996, that was the first where it started in Utsira in Sleipner. So back then it was affiliated together with an oil and gas production. They were producing oil and then they were extracting the CO₂ from that. And then they were injecting the CO₂ back into an adjacent formation, a saline aquifer. And then that's been going quite well. They've been storing about 1 megaton of CO₂ every year since then, which is, roughly speaking, the emissions of 50,000 people a year. So it's quite a significant amount of CO₂, but you still have a tremendous upscaling potential to really cover half of the emissions of the country. So there's still a lot of work to do to actually upscale it to make it sustainable. Now, so we know that hasn't been working for 30 years, so it is a tested and kind of proven technology. But at the same time, we need to be able to monitor it over a very long time to make sure that it's secure and safe, that we can kind of defend this kind of practice over a long time. So the issue kind of comes from the trapping mechanism. So again, you need some sort of seal to trap the CO2 from escaping, right? So that's the basic idea. But you also have other mechanisms at play that are perhaps more secure, or perhaps more important. For example, when you inject the CO2 into some porous media, it gets trapped inside the pores, and you have this residual trapping. It can also react with the brine, the water, and then you basically dissolve the CO2 into a liquid, and then because it's heavier, it will actually sink down. And this is the solubility trapping, and over a very long time, it will even mineralize. And the kind of latter trapping mechanisms are by far more secure, but the challenge is that this takes time over a very, very long time, and you can't really expect this to happen anytime soon, meaning that you need to ensure some sort of safety on a very long time scale. And this has to be then cost efficient to actually make it a reliable upscaling practice. So seismic imaging, which I will cover a bit later, that's kind of standard way of doing CO2 monitoring. It works extremely well, or at least it has been doing that in the past, but it's also very expensive. And then you have all the techniques that people are experimenting with, for example, passive monitoring of sound, basing it more on modeling instead of the actual seismic imaging, kind of ways of getting around the seismic to still be confident that you understand what's happening to the plume. So essentially, the seismic imaging is the most relevant to what I work on here, so I will just explain it a bit more detail, but essentially the idea is very simple. You have some sort of acoustic source. So this image is my AI attempts to explain it. But basically you have a sort of boat, typically that has some acoustic source on it, shooting it into the subsurface. If you're not familiar with seismic and how it works, but basically the sound waves that it generates, they're sensitive to changes in density or velocity of the sound. And the CO2 injected, that is typically in a gas phase or in a supercritical phase, but it's much less dense than the rest of the medium, meaning that once the sound hits the CO2, it comes back in a very strong amplitude. So that's kind of the reason why seismic works so well for this purpose. So to show an example of this from Sleipner, what you see on top left here, this is a cross-section image, seismic image, before they did any injection. So before they started the CO2 injection, they acquired this image, and what you can, for example, see is the dark layer at the top here, which is the caprock. So you see, okay, there's a seal here and everything, so you know that, okay, if you inject below here, you can expect it to kind of rise up, fill up below here, and it will be secure in this region. So that's at least the idea, a bit simply explained, but from this image, that's kind of knowledge you have, right? But then you start injecting, and what's instead happens is this. You see that you inject, and then instead of just going straight up, it starts forming a bunch of layers on the way there. And the reason is because you have a bunch of impermeable layers inside the reservoir that completely obstructs the flow. And without knowing where these layers are, you have no idea of knowing how the flow is going to be, how the distribution is going to essentially end up with. And that is potentially a quite scary scenario, because if you had a layer that is completely impermeable, it could send off the flow to completely wrong direction, and it could send it off to a region where you don't have the same kind of caprock integrity anymore. Now in this case, of course, everything went fine. It still went up, it reached the caprock, so they continued injecting for a lot of years following that, and they continued doing the seismic imaging to kind of check that everything is still as it should be. So this is not the most recent image, but you can see that the CO2 plume still got to the top part, it still reaches the caprock. So all things kind of went well. And today you have way more sophisticated ways of doing the imaging that gives you really high quality images. This image is from a colleague of mine from NTNU, Ricardo Martinez. Basically what he did is something called FWI, or full waveform inversion. And this is really one of the more advanced ways of doing the seismic images, where you're kind of guessing a model and you're kind of checking how well it correlates to your data. But the key takeaway is that at this point, the images are so clear that you can actually start to see, if you look closer, some vertical chimneys forming here. And this chimneys is kind of the key to the whole puzzle that you can see here. because here you just see the horizontal layers. But here, when you kind of have optimized the image to such a high degree, you actually see the chimneys and you see that there are some breaking points in this interlayers, and that's how the CO2 still manages to rise upwards. So it's quite a nice kind of set of data, and you can finally get to this point. But this is again as good as it gets with the best equipment that you can find, and that works great for an R&D example, but it doesn't work for upscaling. We can never do this for every single reservoir and actually make a proper kind of business model out of it. So the challenge is, okay, we still need good predictability. We still need to understand what's happening when you do the CO2 injection, but we need to work with a lot less data than we have in the past. And this is kind of where the lab comes in. So the idea was to then create a lab for CO2 storage and monitoring, where we do experiments kind of mimicking what they do in the field, but inside a controlled environment. So everything inside of our lab is then downscaled by a factor of 2000. So you can see the lab here, and this tank here is where we do the actual experiments. So everything inside here is then downscaled 2000 times. So that means that this lab that is, or this tank that is 4 by 2 meter actually corresponds to something that is 4 by 8 kilometers in the field. So the overall goal of the lab is then to, can we replicate field scenarios? Can we get, for example, the seismic images that you saw before? Can we generate the same from the lab, except now knowing where they come from in a way? And also, can we do something resembling CO2 injection? Can we do injection into porous media, see the same kind of fluid flow, and also do experiments related to that? If we're able to do both of those, then we would be quite far ahead of actually being able to study CO2 storage and monitoring. And of course, once that is in place, we can go further than what you can do in the field. We can try new methods that isn't really proven. You don't understand how they work yet. So you can work on the interpretations. And you can, of course, do things that are completely impossible, create leakages. Of course, you don't want to have in them real reservoir, but you can study them in kind of a controlled, simple environment. And of course, everything here is visible. Like you can take people to the lab and show them how it works, and that's also why it's quite nice for outreach. But in the end, the kind of idea is to create a lab for experimentation around CCS. So I often get asked why we even bother doing this lab experiments, because traditionally people do the field kind of field scale measurements, and they complement that with simulations, and that kind of forms their understanding of how it works. But if you kind of think about how it works, you would have the field scale on one side here, which is kind of the most real scenario. That's exactly how it happens, and that's what you want to understand. But it's also incredibly complex. There's a lot of things that you can't fully capture. There's way too much detail in the actual geology that you can't include in your models necessarily. And in the opposite scale, when you have simulations, you have to cut that away, and you have to simplify it so you don't necessarily have as real scenario as in the field cases, but you have much better control. So you understand, of course, much better what's happening. And the lab experiments would kind of come in somewhere between that. So it's more related to the simulations because it's still heavily simplified. We can't capture all the complexities of an actual reservoir, but we can still contain a lot of complexities. At the same time, we understand everything that's happening. So it's kind of a very nice case where you can do experiments, and you can also relate this, of course, to the simulations. And you can, for example, benchmark simulations against a controlled experiment. So essentially, then what we need to kind of set this up is 3 main components. We need a monitoring system that forms the seismic imaging. We need some sort of geological structure that forms the seal, the caprock, the porous medium, and so on. And lastly, we need something to inject in here, something to replace the CO2 injection. So essentially how we have tried to do this in the lab is that we first create a monitoring setup with ultrasonic transducers. We'll explain those a bit later. And then we have the seal that is made in essentially a solid piece of plastic. There's 3 pieces of plastic that are 3 meters long, and they are 20 centimeters thick roughly. And the idea is that one side of them is machined according to a certain caprock formation. So we're basing this on the same site that I showed before, Utsira. And essentially this plastic is machined exactly to the model that they're using for that reservoir. And these are quite huge pieces. They weigh several hundred kilos and are quite difficult to work with, but qualitatively they capture a lot of the same properties. They're still impermeable, they're still acoustically, they are still dense in the water, so you have the same kind of acoustic reflections and so on. So they actually work quite well despite being quite far from the real place, of course. Therefore, most of the porous media, we're not using one at the moment. We're using water. And I'll also come back to that later. And for the CO₂ injection, we're using air injection. And this also comes back to some limitations that we have in the lab. We don't have the same pressure and so on. So working with supercritical CO₂ is extremely difficult. And CO₂ in a gas phase and air in a gas phase, the difference is not really that important anymore. So that kind of forms the layout of the lab. So schematically, how it looks like is, as you see here, this is from the side, a cross-section of it. So you have the acoustic devices in the top here. So each of these transducers, they are one ultrasound source and receiver. Basically, that means that we can do both kind of measurements, and since we have several hundred of them, we can also acquire data in a lot of different ways. And then you have the plastic, that's the caprock, which is flat on one side and then has like the caprock formation on the other side. And then we do the air injection from below to kind of fill up the reservoir. From top down, this is how it looks like. You have the caprock here, and then you have all these transducers. They're kind of put on a scanning grid, and this whole grid is basically just scanned across the tank back and forth. Then you kind of acquire data beneath it, and then as you scan, you can kind of compile data to form a 3D image in the end. So yeah, so the seismic imaging system. So far, this has been one of the main parts that we are working on, and that mainly we have been interested in. So for that, we acquired one ultrasound instrument. That is kind of actually the same instrument that you would use in medicine, but it has a lot of parallel channels, and we have several hundred transducer, and it effectively means that you can acquire data quite rapidly. And you can acquire it in all kinds of different configurations, meaning that you can do seismic survey quite fast. And then, as I said, we have the scanning mechanism. This is just done with a simple mode at the moment. And here you can see this kind of grid being scanned very slowly across. It's a very simple system, but it works quite well, actually. And in the future, this will also be replaced. So we're already starting on building like two sort of like robot arms that would kind of scan across the tank. And the goal is kind of to make this autonomous, so that you can, or automated, so that you can sit on a computer far away and you can still just program how data should be acquired. And then eventually this data is obtained from the whole tank, and then you reconstruct it into 3D model. If you're not familiar with how this works, essentially the idea is that you know quite well how the kind of sound waves propagate through different mediums depending on the velocity of the medium. So what you can do is that if you have source and receivers in the top, so this is from the cross section, you can very easily simulate how from one certain geometry the sound should kind of spread through the material and come reflected back up again. So then you can compare that with your receivers, and essentially you can just iterate back and forth between a certain model, what you actually record, and do that until these two align, and you know, okay, this model is actually representing my system. So when everything then goes well, you get a data set that you see on the right here. So this is kind of our lab seismic data. So what you're looking at is the caprock, the bottom part. So it has like this wavy feature, which is how the caprock should look like. And then you also see that, okay, there are some parts that are missing, and this is just a feature of the seismic. If you have topography that is challenging, you simply can't image it that well. And of course, this is 3D data, so we can reconstruct it in 3D. So on the right side, you see the actual, the lab-generated 3D model. And then the advantage of working in the lab is that we already know the answer, so we can compare it to the actual model that we have. And first of all, what you can see is that okay, qualitatively it's still fine. You have the flat part on top here, this agrees well. You also see that you have a shallow part in the model, and also in the lab there, and then deeper section. So all good. But if you then start really looking into the details, you will start to see that there's actually a lot of deviations between the model and the lab data. And this is kind of where the seismic becomes quite imperfect. But the advantage is this is very quick experiments. So in the field, you would do this over days and weeks, and it will take, you perhaps have to wait years before you can do your service. But here we can do it in a matter of hours. So we don't necessarily try to optimize the models as much, but we study more the kind of underlying principle, the more basic physics behind it. And advantages, we can do it quickly without test new geometries very quickly and see kind of what works well. So basically, the raw data before you process it essentially looks like this. This is called the single trace. So the idea is that you shoot some sort of pulse into the system and it comes back up again. And then the first pulse that you see here, this is from the top of the plastic that you see there. And then essentially the sound is going to bounce back and forth inside the plastic layer, and this forms the multiples. These are often very difficult to work with in the real data because it's hard to differentiate a multiple from actual interface. But at the very bottom here, we have the interface then to our reservoir, to kind of our aquifer. And here you see a type of two lines. One is the before injection, which is the blue one, and then you have orange, which is after injection. And the reason that they are different is simply because once you inject the air, you have a very low density phase. And this low density phase is essentially going to reflect the sound completely as it comes back up again. So that's essentially seismic in a nutshell, how it works and how we can see if you have gas phase or not gas phase, basically just from this reflection amplitude. So then putting all this together and seeing how it actually looks like in the lab. So the first video is just seeing it from the side, how we actually do the injection. This is taken with a phone, so it's quite poor quality, sadly, but you can see the idea behind it. It's very, very basic and simple. Basically, we just have a tube where we do the injection. We can do it below the caprock, and then essentially the air will start to kind of fill up below this plastic layer. And this is looking from top down, so we can't see the plastic anymore because it's transparent in water. But I've outlined here in the white line. So this is then the plastic pieces, and there are some layers, like some interfaces here, which is the kind of separation between the two different blocks. So our injection point is then here. And then if you start injection, you can very easily see how the air plume distributes. So it's a very kind of simple experiment, but it's extremely useful from the acoustic point of view. Because from this kind of videos, you see exactly the answer. You already know exactly what you're supposed to reconstruct later on. And it allows you to really quantify exactly how wrong you are. And at the end, we have a leakage, and it's not supposed to happen, but also happened sadly in our lab. So yeah, so the next part here is not from my work at all, but I think it's a really cool experiment, and it's very related to what we want to do in the future. So it's called the Fluid Flower Project, and essentially what they did is they also create a lab experiments where they stack different layers of sand with different grain sizes, and by doing that you kind of make some sort of reservoir. And then they injected the CO₂ down here, and I don't know how they did it, but they somehow colored the CO₂ so that you see it very effectively. So essentially, as the CO₂ goes up, it first hits the first barrier, like the difference between the layers, and then it goes horizontally. So this is the structural trapping, right? The second part is that even when it breaks through, you still see that a lot of it is still trapped behind. This is the residual trapping, that it gets stuck in the pore spacing and so on. So they capture a lot of the essence behind the fluid flow just by stacking layers of sand, and did it in a really visual and quite cool manner. And the second part they did that is also very impressive is that they managed to kind of change their activity to happen much, much quicker. So I mentioned before that the CO₂ can react with the water and then becomes heavier and sinks down. And this creates this kind of fingering pattern that you see here. So they managed to make this happen in a matter of just a few hours, probably through some chemical method. But then in this lab experiment, they essentially capture all the different mechanisms that you need in terms of porous media fluid flow. And that's why it's quite nice visualization of the CCS or the CO₂ storage process or lifetime. So the second part they did that is also quite interesting is that they gave this data then to 9 different groups to simulate what they would expect to happen. So basically, they just gave him the initial model without the flow or the results, and they were kind of left to figure out, okay, what would happen if they inject from below here. And what's quite interesting is that all the 9 different groups got completely different results. So a lot of them are qualitatively quite similar, but also still some are completely different. And at least to me, I don't work on this topic at all, but at least to me that says that okay, there's still a lot of interesting research you could do with quite simple experiments. And again, this is done for like a 2D slice, but this is something we also could implement in our lab as well. So for our lab, we have then, like we know from this project, okay, it's possible to do some porous media as well. We can implement that, but the challenge is that it's difficult to do it very realistically. So in this project, they only had the fluid flow and they didn't have the acoustics to think about, and they managed to make it quite realistic. But for us, we can't get the same pressures that you would have in the CO₂ reservoir. You don't get CO₂ condensed into the supercritical phase. We also don't have the temperatures. We have still room temperature. And also, if you want to downscale it down to the actual sizes, like when you downscale the acoustics and so on, you would essentially end up with nanoparticles. And that's not really something you want to work with in a lab environment, at least not on this scale. So there are some practical limitations there. And the second thing is that we want to do acoustics, and that puts on a lot of limitations as well. Because essentially, I didn't say it before, but when you downscale the seismic frequencies from maybe 50 hertz that you would use in the field by 2000 times, you end up with ultrasound. That's why we use ultrasound and not normal frequencies. But the wavelength there is then comparable to the individual grain sizes. So this becomes quite difficult to do acoustics, but then because you get some resonance features and so on inside the sand. But at the same time, you can't use gases. If you use a gas in without compressing it, it's going to basically reflect all the sound coming down. So you can only see one layer, essentially. So we have to use liquid, essentially, to make it work with several layers. So, and also some practical challenges when you do this in 3D. I mean, our setup is 1 by 3 meters, so we have quite a lot of volume to cover. And so that's why before we start doing any experiments in porous media, we need to really know how to do it in a good fashion. So we already acquired different sands to kind of do some same kind of stacking idea. We also acquired some plastic foam. It's way more simpler, but it's something you can form and shape very easily. So it's could be a good like testing material. So this is in the plans for the future, and now the plan is to do it before the summer. But for the moment, it's not really implemented yet. Okay, so that kind of covers the kind of introduction to the lab and what we want to do with it. As the second part of the talk will then mostly be about the research that we're doing, and this goes more in the kind of seismic direction, less about the CO₂ storage part, I guess. But I mentioned in the beginning that one of the main goals of the lab is kind of to show that we can get the same seismic images that we get in the field. And that means that you have to take seismic images after some injection, so you get like a time-lapse image. So you can study the evolution of the CO₂ plume. And it's called time-lapse seismic. So to begin, you start with as first seismic image, which is before any injection. So essentially what you see here is where you feature this is the bottom of the caprock. So again, you're looking from the side now. And on top here, this will be the plastic layer. And then we have an injection point down here. So in the beginning, you're missing a lot of features, like you're missing all the detail here and so on. But this is essentially how the seismic work. When you don't have the low density gas phase, you don't have as good contrast, and you're missing a lot of the more difficult topographies in your medium. But then we can do the injection, start here and inject a few liters of air. And of course, air is buoyant, so it's going to rise up and reach the top part here, and then you immediately see that the deflection comes back stronger, so you have an amplitude increase. And then you can continue doing the injection. You can see that it first fills up the more shallow parts. Of course, it makes sense that it goes towards the higher point first. And then eventually you can fill up the entire reservoir and see that overall the signal has just gotten stronger. So essentially it works quite well in this 2D case. And also works quite well in 3D, of course. So this is now looking top down from like a bird view point of view. So what you see on the right here is the data. So basically baseline minus the monitor. So you do one survey without injection, one after, and then you subtract them and then look at the difference. So ideally, the only difference should be then the air that you injected, right? But in reality, it doesn't work that nicely. So what you see here is that the signal forms a certain shape, and then the white line, that is the actual distribution from the camera data that you see here. So you see that qualitatively they look quite okay, like they agree quite well. You see they correlate nicely. But if you look closely, you will start to see that there's a lot of detection outside of your kind of outside of the plume. So also you have a lot of false positives. And then as you continue to inject, you start to see whether you continue seeing that it still agrees quite well, but kind of the mistakes in data sets starts increasing as well, start seeing points forming outside of the plume. And then eventually you, as you fill up the whole reservoir, you see that for the most part of the signal, it looks fine. You kind of detect signal where it should be and so on. But again, you have a lot of mistakes in data. And this is one of the benefits of doing the lab experiments, that we actually can quantify this, so we actually see exactly where our mistakes are. So to quantify this, then we have to make some decisions on how to kind of say this is air and this is not air, this is an artifact. So we can just apply a simple threshold filter, for example. So within this black line here, this is just our kind of threshold value that we say above this signal value, we think there is air here. And then on the red dashed line, that's where we actually have the air based on the camera data. So when you see it in this kind of quantitative metric, then of course you start to see that, oh, you have a lot of mistakes here, and you start to see that it doesn't kind of line up as well as you would like to. And then to quantify this with a number, we use something called the dice coefficient. Basically, it just maps the overlap between your measurement and the ground truth, the camera data, and it also kind of punishes you a bit for the false positives. So the blue here is the signal data, the red is the camera data, and then the green part is the overlap between them. So eventually, when you get to this point, you start to see that, okay, there's a lot of mistakes there, there's a lot of things you can cover. But in the ideal case, we see about 60% of the plume. So it's not terrible, but of course, there is room for improvement. And in a real field acquisition, most likely the number would be higher, simply because we spend a lot more time working on the model, optimizing everything to kind of make sure there's fewer artifacts. But for a very quick, simple processing scheme, you would have quite a lot of uncertainties. And also one other thing to mention is that in the field, you have multiple sources of information, right? You're not just basing on seismic, you have core, and you have a lot of geological model that you're comparing this to. But here it's pure seismic and no other kind of input into this into the calculation here. So I mentioned in the beginning that one of the challenges we have is that we want to kind of see how little data we can use and still be confident that we understand how the plume distributes. Basically try to do CO₂ monitoring with less and less data. This goes in the direction of data sparsity. The central question is kind of how little data do we need to still see how the plume, see how it migrates. And the idea is, okay, can you reduce the cost of the seismic, because it's very costly? But at the same time, when you just do seismic monitoring for like CO₂ monitoring, you don't also need all the details that you typically have in a seismic data. You don't need all the topographic detail. You just need to know, is my plume where I expect it to be or not? So it's a different question than you would have before. And at the same time, as you reduce data, you get more noise. You have fewer receivers, meaning that the ones you have left, you have to rely on them a lot more. And at the same time, you have less illumination. So you have perhaps some regions that are poorly illuminated just because you don't have proper coverage of them. But the idea is has already been tested. So this is from the field data, not my work also, but it's kind of the inspiration between what we want to do. So essentially what you see is the green and blue region, that's the CO₂ plume from Sleipner. And all the black dots you see here, this is the individual receiver points. So essentially what they did is that they took all data and made like let's say a perfect reconstruction. And then they kind of picked out some of the receivers and repeat the analysis and see so that you actually have still a pretty good image after reducing the data quite heavily. And if you know kind of where the plume should be, you can also place them a bit more intelligently, and then with even fewer receivers, still have a pretty good overview of your plume. So ideally, so in principle, you should be able to reduce data quite a lot and still be confident that you understand where the CO₂ plume is. But again, this is in the field and you have a lot of uncertainties here. So what we thought is that, okay, we can take this, bring it to the lab and try to actually quantify how this works. So the first thing is just to replicate what they did, but with lab data instead. What you see here, this is the same kind of difference image where you take the monitor minus the baseline after taking out half the data. And again, you see the correlation is still pretty fine, pretty much the same as what you had before. And then you can reduce it even further, take away 90% of the data. So you're left with very few receivers, and you start to see, okay, some of the noisy parts is kind of picking out and being now detected as air. And eventually when you remove 97%, basically almost all the data, you're left with a completely uncorrelated picture. And 39% overlap, that's essentially what you have if you have a completely randomized detection system. So if you then put this, well, first off, we get kind of this voltage the same as what you have in the field. You still see that even when you reduce 90%, you still have a relatively okay image of your plume. But we can quantify it and actually put this in a plot. And essentially what you see here is first, y-axis is the overlap or the detection percentage, how much of the plume you're detecting. And on the x-axis is the amount of data removed. So in the bottom, in 0%, that basically means you have all data, 100% means you don't have any data. And what's quite interesting is that you actually see that as you remove data, you don't really change the detection at all. It stays more or less constant, but a slow decline. And at some certain critical point, you completely lose all detection and it becomes random very quickly. So it's a highly nonlinear correlation between the detection and the amount of data to use. So yeah, we tested this for a bunch of other kind of geometries as well. Not go too much into detail here, but essentially we try to remove data in different ways. We also try to kind of challenge it by adding noise to the signal. We try to add some noise to the positioning and so on. Like if you had some sort of uncertainties in your acquisition, and then basically try to see how well data can still be decimated if you had much worse quality. And yeah, I will not go too much into results, but you can see that the trends we see is very, very different depending on the type of decimation and the type of quality of data. So with that being said, this lab is continuously evolving. Like we continue building it for different purposes and trying new types of experiments. Mostly what I've been talking about today is the kind of CO₂ monitoring strategies. But I also mentioned that we want to include the porous media to kind of make it a bit more realistic. And at the same time, if you can do both some sort of fluid flow with porous media and acoustics, you essentially have some sort of multi-physics experiments that could be very interesting, because the seismic has a lot of uncertainties. The porous media simulations, for example, and would have a lot of uncertainties. And if you can kind of study how this would meet, you would have a very interesting study case, I think. And the last part is that we want to make this more autonomous, so that we don't actually have to be in the lab. So the idea is that this is supposed to be like an open access infrastructure that is available to anyone. And the idea is that hopefully by the summer it will be so automated that you can actually just sit on a computer anywhere in the world and just kind of plug in the kind of experiment you want to do and do it. We'll see how it works out. I will give it my best effort, but that's the plan, at least with the lab. So yeah, that's all I wanted to say. So the kind of bottom line is that we want to create a lab experiment for doing CO₂ storage and monitoring. It's of course very simplified. It doesn't capture all the realism of a real reservoir, but we do think that if you design it in a kind of inaccurate way, you could still do a lot of experiments that you could never do in the field and quantify a lot of things that have before just been qualitatively done. And it's continuously evolving. We continuously try new sort of experiments and try to expand continuously what we use the lab for, essentially. So that I also just want to thank all the people who has helped me here in the research. A lot of people have helped me physically in the lab because it's a lot of work to do it. Also, I've been helped a lot by Philip and Martin with the overall project itself. All right, so thank you all for listening.
Thank you very much. Any questions?
I have many. So since this is an environmental institute, probably there are some people working with fishes, and I was wondering, I think it's a bit aggressive or damaging for the fishes when we do this seismic or acoustic surveys from the ship. I was wondering if, so in the picture of this northern lights, you are showing we have the pipeline on the seabed to bring the CO₂ to the injection point. Would it be possible to have acoustic like fiber optics or something to replace this kind of surveys with the ship? And
yeah, I mean,
maybe you can also test in your lab experiment.
Yeah, I mean, what you're referring to is passive monitoring, right? And it's probably the direction we're going with the seismic. So instead of doing the seismic imaging, creating the kind of shock waves, we instead just measure the passive sound and using that to try to see what is changing and use that to infer the CO₂ monitoring. And I think this is already being tested now. I think it's more on the research scale, like it's not really implemented in the bigger projects, I think. I'm not sure, but it is definitely possible. And a lot of, I think, production wells in oil and gas production, they also have the fibers inside the wells to also use that to monitor pressure, for example, and yeah, also just try to squeeze out more information, basically. So yeah, it's definitely possible. And also it would be much better for the environment if you didn't use the active sources. So I think it's definitely possible, but probably requires more work on the processing part.
And then another question, I was wondering about the choice of injecting air instead of, because so when we have the supercritical CO₂, the density is around 650 kilos per cubic meter, but with air it's very little. So the density contrast is huge.
Yeah.
Have you thought of using another liquid that has a density at room conditions of around similar to the supercritical CO₂?
Yeah. Yeah, so we have that in mind. The reason for using air is more that the acoustic contrast is not as different as you would expect if you just look at the top layer. And it's very practical to use it. But I think long term, what we want to use is more similar to oil, like a mineral oil, or even just salt water actually could work. Salt water and normal water to kind of get this density contrast that would be more realistic. But the challenge is that once you do an injection, you would have to clean it out. So you can't just repeat experiments, then you have to actually really carefully design how the experiment should be. You have to try once and you have to hope that it works at one time, because resetting it is going to be a lot of work. But I think in a month or two, that's something we will try. So first we have to build a porous media, and then I think we'll find a fluid that also would work better.
Thank you for your presentation. It's very interesting and it will be very, very useful lab. I was wondering about, you mentioned that you want to include the grain size and materials, or you already did it?
What do you mean to include the grain
Because,
size?
because you have the caprock
Hmm.
and then it's water,
Yeah.
completely water, but do you include the grain size of some materials already, or do you?
No, at the moment it's just water.
Okay.
So we will add the porous media in the future. But the reason is that for the kind of monitoring purposes, the porous media just changes the density, right? It doesn't really affect the seismic processing techniques you would use. It doesn't really affect the results as much as you would expect. It's more for the fluid flow that would be more realistic if you had the porous media.
Because I was wondering about the equivalent volume that you will have, because it depends on the grain size that you include. It completely changes, and it affects in the wave that you obtain, the grain size that you will include.
It affects in the wave.
Yeah, when you receive the wave.
Yeah, like it's a grain size matter for the reflection.
Exactly. Yeah.
Yeah, it does matter. Typically, if your wavelength is way larger than grain size, it just becomes like an effective medium, and you can do some approximations, and then it becomes less and less important. But as the wavelength kind of becomes the same size as the grain size, then you get some resonance features, and essentially the sound attenuates extremely quickly.
Because if you want to include sand,
Hmm.
sand has different compositions, but if you include silica or glass, then with very, very tiny, maybe this could be useful to.
Yeah.
I don't know.
Yeah, that's of course another option to just not use sand, but some other compound. There's no specific reason for sand. I think it's also practical reasons. And I also bought the sand before I arrived, so I couldn't really influence that.
Because you have in the sand, you have quartz, feldspar, mica.
Yeah.
So, for instance, if you have mica, a lot of composition will be very relevant because it's a laminar mineral. So
yeah,
it will be for the ref resolution in that place is 1 meter, right?
Yeah.
It would be difficult to manage this.
Yeah, I mean that's a very good point, especially when you have some facets and so on the grains. At this length scale, that would actually matter a lot more than it would do in seismic in the field. So yeah, it is absolutely good points. Yeah,
we can talk later. Thank you.
Okay, so thank you for the presentation. You showed how the results of the extent of the plume is changing with data reduction in your lab study. How do you feel if the same results can be derived in real field conditions? Do you have to change anything in the properties of the reservoir, in the impedance from place to place? Do you think if the results would be still valid in those cases?
I think quantitatively they would be different, but the underlying idea I think would be very similar. Yes. I mean, of course, in a real field case, if you really want to do it carefully, you go through it a lot more with a lot more processing steps, and most likely you can push the kind of quality to with a lot less data. But you still have to work with the same data, and if that data in a very basic processing scheme shows a certain trend, it's unlikely that different processing trend and more time spent on it is going to qualitatively change it. But of course, quantitatively, yes, it will be different.
And what's your idea of how it could help? I mean, when you have basin with multi-site injection, then, for example, having seismic monitoring a couple of injection sites and then kind of extrapolating to the other sites, which is also in time as well. In time and space.
You mean how to kind of reduce data in time and space?
How such kind of data reduction and help
I mean,
support it to the basin scale imaging.
yeah, I mean, I think it could help in kind of understanding the overall idea when you reduce it, because if all you're basing it off is field data and you see changes in your data as you reduce it, you don't necessarily know how it's going to work on a general level, right? So you can try designing a project with less and less receivers and you can get some results, but I think the results here can already give us a point to the fact that there are very nonlinear effects at play. But I think beyond that, you still need to evaluate specific cases, case by case. I don't think you can find a single overlying trend for every single reservoir. So it will still be a case by case thing, but hopefully the results can still give a point to look at what kind of qualitative features you should look for as you reduce the data.
Any other question? Okay, so we can leave it here. Thank you very much again.